In this video, I'm going to prove a very interesting fact. Phi of n is a perfect square for infinitely many integers n. That's pretty amazing statement. Proof isn't that bad. Talking about proofs, welcome to Nothing But Math Proofs channel on YouTube. If you're into watching mathematical proofs, you should consider subscribing to my channel. Okay, now if we consider n equal, say, 2 to the 2k plus 1 for any k, say, bigger than 1. I guess it can even equal 1. So phi of n, or phi of n, excuse me, is phi of 2 to the 2k plus 1, which is 2 to the 2k plus 1 minus 2 to the 2k. And we can factor out 2 to the 2k. And we're left with 2 minus 1. 2 to the 2k is 2 to the k squared, perfect square, times 1. That's also a perfect square. So, but I'll erase it, but 1 is a perfect square. So now, what I showed is that there's infinitely many n's. And for any k bigger than 1 or equal to 1, I can find phi of n, if it's in this form, to be a perfect square. But do you have to use the number 2? So before I go on, the proof is done. There it is. I found infinitely many n's, 1 for each k. So I found infinitely many. But can we think of others? Well, if you consider the prime, if you consider the prime 3 and you take away 1, you don't get a prime number. A perfect square. If you consider the prime 5 and you take away 1, you do get a prime number. If you do 7 minus 1, 6 isn't a perfect square. 11 minus 1, no. 13 minus 1 is 12, no. But 17 minus 1 is a perfect square. We can play this same game with 5 and, say, 17. For example, if you consider phi of 5 to the 2k plus 1, you will get 5 to the 2k plus 1 minus 5 to the 2k. And if you factor out 5 to the 2k, you'll be left with 5 minus 1. Now this number is 5 to the k, which is an integer squared, times 4, which is a perfect square. So we get 2 times 5 to the k squared. And that's because, not because I got a perfect square here, but n, the base minus 1 is a perfect square. 5 minus 1 is a perfect square. Now, if we play this same game with 17, we're going to get 17 to the 2k plus 1 minus 17 to the 2k. And if I factor out 17 to the 2k, I'm left with 17 minus 1. 17 to the 2k can be thought of as 17 to the k for some integer k. That's going to be a number, square. So that's a perfect square. And look at this, 16. That's 4 squared. So 4 times 17 to the k all squared. That's what we would get for phi of 17 to an odd power, 2 to the k plus 1. Okay, so it doesn't only work for 2. Again, any prime number, 19 minus 1, is not a perfect square. 23 minus 1 is 22, not a perfect square. But 37 is prime, and if I take away 1, I get 36. So that's a perfect square. So we can play the same game with taking phi to the 37, phi of 37 to the 2k plus 1. This is gonna equal to a perfect square. Again, the trick is we can always get this to be a perfect square. The question is what's left over gonna be a perfect square? And the answer is if one less than this number is a perfect square, then it will work. That completes this video, or the proof of this theorem. Actually, the proof, as I said, was done a little bit earlier, but then I gave some more examples. If you like seeing mathematics like this, subscribe to my channel. This is all we do here, mathematical proofs. See you guys in the next video. Leave a comment, click the like button, share my videos, and most of all, never forget, keep watching and learning.